Logic and reasoning are related, but they're not the same thing. And a lot of reasoning depends on logic, but logic is the study of ideas that will give you more logic. Has nothing to do with if it rains tomorrow, I'm going to have to buy a lottery ticket, which is reasoning. And we study reasoning because that's why we study anything, is to study reasoning. And we study logic to help us with reasoning, which it does, but partly we study logic because it's a good introduction to what's called Boolean algebra, and that is an important part of computer science and understanding everything that has to do with computing the way we do it, especially with circuits and other design problems. So Boole was an Irish mathematician, and he died in 1864. So let's just say he was way ahead of his time, but that's partly why we're doing this, is so that we can get some practice with Boolean algebra. So where we begin with this is a basic definition, which is the definition of a proposition. And a proposition is a sentence, so this is kind of a grammatical description, and it is either true or false. No, you may not know, but there's no in between. So it's either true or false. And so I might get an ice cream tomorrow. That's not a proposition. There's no way to assign a definite true or false value to that. If I say, if they have strawberry, I'll get an ice cream, that is a genuine proposition. So we can decide whether that's true or false. That would require more reasoning rather than just the bare bones true and false. But propositions are what we do reasoning with. And the way we represent the basic ideas of logic and Boolean algebra as might be applied to reasoning is with a truth table. And so we're going to construct some truth tables to help us understand the basic logical operations. So we're going to take that we have two propositions, P and Q. We'll start with two. And we're going to make a notational convention that 0 means false and 1 means true. So in a lot of programming languages, 1 is true is also built into the language, especially in things that are derived from C, which would include C++ and Java and the like. So 0 is false is 1 and 1 is true. And we have two possibilities for P, and we have two possibilities for Q. So there are four possibilities of how this truth table might be arranged. And there are two conventions. There's the standard convention and there's our textbook convention. The textbook convention makes sense because what they do is arrange the rows of the truth table as 0, 1, 2, and 3 in Boolean. But for 160 years or something, people have arranged truth tables this way. So tradition dries hard. Yeah, it's like you got to keep it wet, I guess. Anyway, there are going to be four things, and there's a standard way to do this, and we do this backwards in the order that we've written them. So Q can be 0, 1, 0, 1. So that there are going to be four possibilities for the values of Q. So we do that in singles. P is 1, 1, 0, 0. We do that in doubles. If we had a third variable, we would be doing that in quadruples, not triples, quadruples. And we'll show you an example of that in a minute or something. So these are some basic ideas. These are the variables. And P is 1, Q is 1, P is 1, Q is 0, etc., etc., etc. So what we have is a function, and this is kind of why these things come up so prominently in computing, is that this is a function on bits. Okay, so the first thing that we're going to do is, I'm going to write this two different ways because there are two different ways that people write it. So is negation. So the symbol for negation is this funky little L or a tilde. Either way, you can you can say that you're going to negate something. And so if P is true, its negation is false. If P is false, its negation is true. So I'm just going to fill in the truth table. This is now based on, this is going to have duplicates because there's only one variable involved here. So the values are 0, 0, 1, 1. And in each of those rows, I've negated P. So there's negation. The next one that we should talk about is and. Oh, excuse me, conjunction. And so let me make a note of that. I'll tell you what, a lot more people say and than say conjunction. And so there we go. I'll fill in what I said about negation either. Now, P and Q is true if both P and Q are true. If either one of them is false, then that's not the case. And so the truth table in the standard way of writing it is the only place where both P and Q are 1 is in the first line, and everything else is 0. This kind of looks like binary multiplication, doesn't it? 1 times 1 is 1, 1 times 0, 0 times 0, 0 times 0. Okay, there's something to that. So, okay. So that is conjunction. The next one is or. So this one is true if either one or the other, or both are true. It's not exclusive or. This is just ordinary or, as opposed to exclusive ordinary or. And so I think it's disjunction. These are words that I never use, and so sometimes you'll hear them from people, but that's okay. So just filling in, if either of the variables is 1, then or of those variables is 1. And the only case where that fails is in the bottom line, the way I write it, where they're both 0. So this is 1, 1, 1, 0. Bingo. Okay. The next one is the one that gets everybody's hackles up. And there's a good reason why it gets everybody's hackles up. And I'm going to write it two different ways because it's commonly written two different ways. The first way is the way the book writes it, with a single horizontal arrow. Most people say a double horizontal arrow. And so this is implication, and I'm thinking some not nice words. Implication is very confusing, and so I'm going to write it down, and we're going to worry later about why this is the correct way to talk about implication, which is controversial. But the values are 1, 0, 1, 1. So this one makes sense. If P and Q are both true, then P implies Q. Yeah, that would be true. If P is true and Q is false, well, then that implication is false. If you have something that's true, it doesn't imply something false. And so that's the basic reasoning part. The part that gets everyone's hackles up is that if P is false, it doesn't matter. The implication is true. And there are a lot of different ways to explain this. None of them are fully satisfactory. And sometimes I feel like what we ought to put here is irrelevant, because these don't arise much in practice. On the other hand, this is a legitimate Boolean operation, and so we should consider it. But let me run this one by you as another legitimate Boolean operation, which is random. You could just put any random set of bits here, and so I could just say 0, 1, 0, 0. And this might or might not have something to do with some kind of combination of these various logical operators, or it could just be random, and that is a gateway to a lot of interesting questions about computability and the like, including the NP versus P problem. And if we have a little time at the end, I'll mention something more about that. So anyway, but these are the useful ones. And so that's the situation. If we had three, let me just write this down lickety-split. If we had three, so let's call the propositions P, Q, and R. And the way to do this is, well, it's going to be 2 cubed. There are three things, and there are two choices for each of them, so there are 2 cubed choices. And the way to write this down efficiently is just say 1, 0, 1, 0, 1, 0, 1, 0 for R. And then next time you do them in pairs. So for Q, it's 1, 1, 0, 0, 1, 1, 0, 0. And the next time you do them in quadruples, if there were 4 variables, the next one would be in octets, something like that. Anyway, so but now it's a quartet. So 1, 1, 1, 1, 0, 0, 0, 0. Remember, you don't have to worry about copying this down. I'll scan this for you. So this is how you would make a truth table for 3 propositions. And if you look through here, you'll find all of the binary digits from 0 to 8. So they're there. So the order that's in the book makes some sense, is reasonable. I'm not sure it's logical, but it's reasonable. And this is also reasonable. I'm not sure it's logical, but it's reasonable. This one's a little bit easier to generate. So there's the situation. Okay. Couple of things that we can do with these just to kind of get started is to start to move things around. So let me give you a couple of more definitions. The first is the definition of converse. Yeah. The converse of P implies Q is Q implies P. You change the order. It has a different truth table, but which you could work out, but it's the converse. Those are certainly not logically equivalent. This is where we're doing some logic. Those are not logically equivalent. And so if the implication is true, the converse may or may not be true. It depends on what's going on with the individual variables. So that's the converse. And that's not the one we use the most. The one we use the most is the contrapositive. You'd think you'd call it negative or something, but we've already used that. So contrapositive, and the contrapositive of P implies Q is the negation of Q implies the negation of P. And so I'm using the more standard mathematical idea of negation, but this is an important tool in doing reasoning because these are absolutely 100% equivalent. If you write out the truth table for this, then you'll find that the contrapositive and the implication have exactly the same meaning, exactly the same truth values, and so they're quite related. So these are the same, which is a very useful problem-solving strategy. You say, oh, if P implies Q, oh, I don't know how to do that. But not Q implies not P. That might give you actually an easier path to describing the problem that you're looking at. Okay. And finally, we get to the biconditional. Which is commonly called if and only if, or IFF, and that is written as a two-sided arrow. So we have P, two-sided arrow, Q, and what it means is P implies Q and Q implies P. So it goes both ways. And so those are completely equivalent. So, a couple of things to kind of finish up. On page 42 of the textbook, there's a list of equivalent ways of saying equivalent ways of saying equivalent ways of implication. It's a long list. It's a thing that people sometimes do to kind of confuse other people because maybe it sounds like it's implication. and maybe it isn't implication. And so in doing reasoning, in trying to understand whether implication is going on, using this list can help you decode what someone's trying to say. This is strictly a question of natural language, not a question of logic. It's about reasoning, not logic. So there's that. And then the last thing I want to mention, which is a look ahead to a big issue in computing, is the P equals NP problem. And this isn't the place to go into this in a lot of detail, but basically a problem is in class P if it can be solved in polynomial time. We have to say more about that later, but that's considered feasible. In practice, it isn't always feasible, but in theory, it's what's feasible. NP is the class of problems that you can check in polynomial time. You may not be able to do them in polynomial time, but you can check them in polynomial time. And so this is a matter of algorithm efficiency and feasibility. So the idea is with NP is that you can take a guess and then check it. And the checking is feasible. But if you try to actually solve the problem, you may not be able to do it within the remaining lifespan of the universe. So the question is whether class P and class NP are the same. There are a lot of people who have a lot of feelings about this, and I'm going to leave that out. But I want to mention the kind of primary example of an NP problem is, everyone says SAT, S-A-T, and that is satisfiability. And SAT says if you take a really long bunch of implications, blah, 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 I'll say like I'm going to do 101 of them, and now connect them with logical operators, or let's put an and an or and an implies and a negation and an equivalence or something. So now this looks hard, because if I have n plus 1, why did I do that? Oh, I'm sorry, if I have 101 variables, the number of possibilities, the depth of the truth table is 2 to the 101 power, which is really big. 2 to the 10th is about 1,000. 2 to the 100th is 1,000. This doesn't feel so good. Anyway, it's a really big number. So you're not just going to write out the truth table. And the question is, can you find values for P1, P2, and P3 and so forth, such that this whole thing is true? So the question really is that kind of random expression ever true? And that's the satisfiability problem. It's an NP problem. If someone gives you values, you can plug them in, and it's only going to take, in this case, 101 operations. That's nothing in the computing world. And if you had to try to find one, well, that's going to take until the end of the span of the universe. So this is an introduction to NP problems and the P versus NP problem that comes from Boolean algebra, which is the basic thing that goes into how computers work. So this is not some kind of egghead problem. This is something that people who really do things worry about.